In this video, we will be discussing the two types of bonds that we will be considering using valence bond and molecular orbital theory, the sigma and pi bonds. A sigma bond results when the interacting atomic orbitals point along the axes connecting the two bonding nuclei. This axis is sometimes called the internuclear axis. Either standard atomic nuclei or hybrids can form sigma bonds. When you have two S's overlapping, two P's as long as they're pointing towards each other along the internuclear axis. Two hybrid bonds, you could have an S and a hybridized bond, etc. The key point is that the two orbitals are overlapping along the axis that is between the two nuclei. A pi bond, on the other hand, results when the bonding atom orbitals are parallel to each other and perpendicular to the axes connecting the two bonding nuclei. So they are parallel to each other, but perpendicular to the internuclear axes. These pi bonds are only between unparallelized p orbitals. The interaction between parallel orbitals is not as strong as between orbitals that point at each other. Therefore, the sigma bonds are going to be stronger than the pi bonds, and this is because of the degree to which they overlap, as we will see in the following images. One of the primary differences between the sigma and the pi bond are the orientation of the orbitals that are used to make the sigma and pi bonds. Let's say we're working with just pi bonds for now. We'll take a py here. This one we'll say is a py and another py. So they are both laying along the y-axis, and they come into interaction. They're between two atoms that are trying to form a bond. There isn't a direct overlap when we move these closer to each other, but instead you have this parallel interaction where you have the electrons from one get shared with the other, and they form these two lobes, one above and one below the bonding axes. So it's sort of a meshing of the top orbitals and a meshing of the bottom orbitals to get this overall, what we will call a pi bond. Sigma bonds, on the other hand, we could make them out of p orbitals. So let's say we have two sets of px's, a px on one atom and a px orbital on another. When they come close together, you'll have an overlap between the two orbitals that are directly in between the two nuclei. When you get this overlap, you end up forming a sigma bond. A sigma bond is one in which there's a lot of overlap between the two atoms, and it's along the bonding axes. We could also have sigma bonds that use not just p orbitals, but sigma and hybrid. So you could have an example of where you have a sigma bond, which would be spherical, and a hybridized orbital, which looks somewhat like a p bond, but has a large lobe on one side and a small lobe on the other. When these two come together, you would see a direct overlap along the axes between them. It looks like that, and it's this direct overlap right here that gives you the sigma bond. So, because the pi bond occurs directly above and below the internuclear axes, again the axes between the two nuclei, and the sigma bond occurs directly along that axis, you can get a situation where a pi bond is above the axes and you have a sigma bond below. This is the case of how double bonds work. A double bond is a combination of a sigma bond in the middle and a pi bond that is above and below the axes. It is the overlap between hybrid orbitals on one atom with a hybrid or non-hybridized orbital on the other atom that will result in a sigma bond. That's what we have down here between our carbon and our oxygen. The overlap between the unhybridized p orbitals on the bonded atoms is what gives us the pi bond. So you have two p orbitals, one from the carbon, one from the oxygen. They come together to give you your pi bonds. Hybrid orbitals overlap to form sigma bonds, and unhybridized p orbitals overlap to give you your pi bonds. Because the orbitals that form the pi bond point along the internuclear axes, rotation around that bond does not require the breaking of the interaction between the orbitals. So if we only have a single sigma bond between the two atoms, because the overlap occurs directly between, one of the atoms can rotate, maintaining that overlap. So our sigma bonds are free to rotate. But the orbitals that form pi bonds interact above and below the internuclear axes. So if we wanted to rotate something with a pi bond, we would have to break the pi bond in order to do the rotation. As a result, things that have pi bonds do not rotate. A pi bond is what makes the second bond of a double bond. The first bond is a sigma bond along the internuclear axes. The second bond of the double bond is a pi bond that is above and below the sigma. Because it is above and below, in order to rotate, you would have to break the bond. So double bonds do not rotate, whereas single bonds do. Where this matters is for isomers. Isomers are chemical compounds that have the exact same chemical formula, but a different arrangement. So we could have what we call the cis transformer. This is where your important compounds, in this case the chlorine, are on the same side of the double bond. Or we could have the trans isomer. The trans means opposite, so we have the chlorines are on the opposite side of the double bond. Why this is important is if we're trying to determine polarity of these two molecules, the cis isomer has dipole moments that are going to be pointing towards the chlorine. So the two dipole moments are going to add together to give you a larger overall dipole moment, making this one polar. For the trans isomer, you have one dipole that's pointing that way in a bond and another one that's pointing the other way. When we add these two together, they cancel each other out. The one down here is going down and to the left, and the one up here is going up and to the right by the exact same amount. So when you try to add the two together, they cancel out and there is no net dipole. So this is non-polar. So depending on where the substituents or the groups that are attached to the chlorine are, you could have a polar molecule or a non-polar molecule, even though it has the exact same chemical formula, depending on what the configuration is around the double bond. And because double bonds don't rotate, these two substances do not interconvert. So your cis 2-dichloroethene is different from your trans 1,2-dichloroethene.